Okay, my name is Charles Jennings. I'm director of the Christian Regenhard Center for Emergency Response Studies, and we'd like to welcome you to our first seminar of the spring 2021 semester. For those of you who aren't familiar with the center, and I know we have a number of new visitors, we are an applied policy research center that's focused on response of uniformed services to large-scale and complex events. And we pursue interdisciplinary applied research in that area. And we do the seminar series as a part of our education and outreach, which includes research and curricular activities as well. We would encourage you to join our mailing list, which you can do by clicking on Contact. And then Join Now, which takes you to join our listserv. We also have a Twitter feed, and our Twitter handle is RaCERS JJC. And so we'd just like to welcome you. Today's talk is we're really pleased to have our guest, but at first I'm going to turn it over to our MC, Glenn Corbett. Glenn Corbett is on the faculty at John Jay College of Criminal Justice in the Department of Security, Fire, and Emergency Management, and is also technical editor for Fire Engineering Magazine, author of Brannigan's Building Construction for the Fire Service. But Glenn is happy to have him today.
Okay, well, thank you, Charles. And thank you all for attending today. I think we've got an exciting presentation coming up from Dr. Ashrafi. This is a topic that is particularly relevant today, particularly where a lot of things are happening at the, really at least within our country, within the United States, at the national level, when it comes to performance-based designs and fire protection. And in the case of today's presentation, the interrelationship between structural fire protection engineering and the fire service. It's something that many of us in the fire service are very interested in. I think, having talked with Ali and other folks who are in the structural engineering realm, there's a natural alliance between firefighters and structural engineers. We both want the same things. We both, of course, want buildings to stand and stay up, particularly during a fire event. So before I start and read Ali's intro, his bio, I just want to call your attention. Charles mentioned earlier, I'm technical editor of Fire Engineering Magazine. It's a 145-year-old trade journal, one of the oldest in the country for the fire service. We have an article in the January issue, which is actually entitled, funny, Earth, Wind, and Now Fire. It was co-authored, myself and co-authored with Kevin LaMalva. Some of you probably know Kevin. And it's sort of the first, perhaps in a series of articles about, again, this relationship between emergency services, particularly the fire service, and the structural engineering field. So let me give you a little background for those of you who don't know Ali. He received his PhD in civil engineering and engineering mechanics from Columbia University. And he's currently a principal at Thornton Tomasetti here in Manhattan. He's the vice chair of the American Society of Civil Engineers Fire Protection Committee. And he's a member of the American College of Engineers, American, I'll get it right, Ali.
ASEC is American
Council of Engineering Companies, right? Okay.
Yes.
Okay, that's a long one. It's a long acronym here. Metro Fire Region within that organization's Fire Codes Committee. He's overseen a bunch of projects, including investigations as well, particularly investigations into post-fire, investigations into building response to fires. He also has designed several projects, particularly in the realm of performance-based structural and fire protection engineering, including iconic structures such as the Shed in New York City, the Seaport World Trade Center in Boston, Pittsburgh's International Airport, and the Kravis Center in Florida. He's also an adjunct professor at Columbia, where he teaches both structural fire engineering and earthquake and wind engineering. So without further ado, I want to bring Ali on to give a PowerPoint presentation. At the conclusion of that, he and I'll have a short discussion, some perhaps hopefully relevant issues, and then we're going to open it up to the audience for you folks to ask whatever questions you like to ask. I have to make one last note. I have to actually teach a class at 3 o'clock. So if you see me disappear, it's not because of the topic today, or certainly because of our speaker. It's because, unfortunately, my students are expecting for me to show up. So anyway, without further ado, again, Ali, thank you so much for coming today, and the floor is yours.
Thank you for the kind introduction, and I'm very excited to be here. Let me start sharing my screen, and we'll go from there. Do you see my screen?
Yep, you're good, Ali.
Okay, so thank you again for having me. I'm very excited to be here and having this conversation. I'm particularly excited to have this conversation at RaCERS Center because the focus of the center is what I'm talking about, which is large, complex events. And that's where I think we have gaps in fire safety that are particularly relevant to firefighting and firefighters. So the point of my discussion today is that relationship between design and what it means for firefighting. I do look for this as the start of hopefully a conversation. I know there are a lot of people in the audience who have dealt with fires and do that on a day-by-day basis. So I do really look forward to lively discussion and feedback from you at the end of this presentation as well. So with that, let me get started. So why are we having this conversation? So the way we're designing buildings for fire safety determines what happens in the fire. They're not independent things. How we design determines what a firefighter will face in a fire. And the common practice in the design has substantial limitations when it comes to fire safety. And those have an impact on occupants and firefighters, especially when it comes to more high impact buildings. And at the same time, we know that we can have designs that are safer, but those designs are not as common and they're not required by the code. They're permitted by the code, and even there, it's a long process. Now, this discussion, I use the word design, but the discussion applies to both new design and existing buildings. And I will make separate points about what this means for new design and also what it means for firefighting in the context of existing buildings. And bottom line for me is, to me, this is a start of a conversation. We have a lot of people who are involved in fire safety. That includes fire departments, building departments, design professionals, the construction industry. So hopefully this is a conversation that leads to better and safer designs. And so for this presentation, I will provide a quick description of the current design limitations and then an outline of what the solution would look like. And then we will have a discussion about the perspective of different stakeholders that are involved in this process, and also talk about what are the implications for new designs, for existing buildings, for the firefighting in the sense of operations, research, or training. I do want to make a point here that although the discussion is broad, my focus will be on the less frequent but more impactful fires. So that's the focus. On smaller, more frequent fires, I think we've learned a lot from experience, and we know a lot more about how to deal with them. So what is the common practice? The common practice is prescriptive design. And what that means is that the code tells you what materials to use and not to use, and where to put it, and how to tie it together. So you are following the instructions of the code to result in a building. What it doesn't do is quantify what happens in a fire. So you don't analyze what will happen, and you don't have any sense whether the consequences of a fire will be acceptable. It's presumed that once you follow those prescriptions, you'll get a safe building, but you don't actually design explicitly for that. And when it comes to the question of stability of buildings in fire, that's a question that's not answered. That's a question that's not asked in the prescriptive design process. There's zero analysis involved in that. Okay, so now to put prescriptive design in context, this is what it would mean for us to design a shuttle using a prescriptive design. It means that you would be using specifications and testing procedures that are from previous generations of shuttles. Although now we're dealing with shuttles that have a different size, they have different materials, you're trying to get to a different location, you're using different fuels, but you're using that older set of instructions to come up with your design. And we provide component specifications. For example, the specifications would tell you have this tonnage of fuel within your shuttle, and the thickness of the exterior of the shuttle shall be this much. But you do not specify performance goals. So you do not say, okay, design such that the combustion gives you enough force so the shuttle can escape gravity. Design such that the heat of combustion and re-entry does not burn the shuttle. Those would be things that we actually care about. They're performance goals. Those are not specified in a prescriptive design. And then once we've tested individual components, we don't do any analysis of how they work together as a system when you assemble them into a shuttle. That would be prescriptive design of a shuttle. I don't think that would not be a good process. That's exactly how we're designing buildings for fire. So we use testing and a design framework around the concept of fire resistance ratings, which was developed a little more than 100 years ago. And in that time frame, the size of the buildings has changed, the materials that we used, the construction techniques, how we design the buildings, what is the layout of your floors, what do you do inside the buildings, and what goes inside the building and forms the fuel. All of these things changed while our design process and the framework is basically the same. And then within that process, we specify component specifications. For example, your individual elements, your beam or your column has to have this much fire resistance as defined in code. Your sprinkler has to have this much capacity. Your standpipe shall provide this much water access. Or your means of egress should be this wide. Those are all prescriptive. We tell how to build the building. But we do not specify performance goals, which would be telling, okay, your building should stand up for this duration, or people should be able to evacuate within these many minutes and either shelter in place or evacuate the building entirely. Or saying that the fire protection systems within the building should provide enough water so that you can fight a fire of such size. Those are performance goals that would be actually useful in terms of understanding what will happen. Those are not specified in the code. And when it comes to structural stability, there is zero requirement for analysis. That's the prescriptive design of buildings for fire. And that's a process that I want to highlight compared to not having that has improved safety, right? Having fire resistance is good. Having standpipes that provide some water is good. Having some requirements on egress is good. And for buildings that are smaller and fires that are more frequent, we have enough experience to know where the gaps are. The question is when you are stepping beyond that range. Now, when it comes to firefighting in buildings, it's really important to pay attention to the fact that the building is the battlefield. That's where you are doing your process. So whatever happens to the building has a real impact on firefighting, and that building has changed substantially over time. As a firefighter, the goal is foremost life safety, right? And that includes the occupants, it includes firefighters and the public. And then after that, you have the goal of minimizing damage to the building, to the contents, and to the community. And there is interaction between these. If there's damage to the building when people are inside of it, or that impacts the area, obviously that's also a life safety question. Now, there's a higher risk. When there's a higher risk to the people inside the building, that means that the firefighters will also have to take higher personal risk to go and rescue people, right? So to the extent that the design allows for, the design increases the risk or reduces the risk to the life of people, that directly increases or reduces the risk to the life of firefighters who are trying to do that. So better design can simultaneously reduce the risk to life for firefighters and the people inside the building. And the key here is knowledge of what to expect. If you are a firefighter and you're trying to fight a specific fire, you need to understand the risks, you need to understand the timing, and then you can make informed decisions that are based on those risks as opposed to making assumptions. That battlefield, the building, has changed substantially over time. We're building structures that are taller, larger, leaner. They have wider spans, and they have different construction techniques that we used decades ago. It's quite common to have open floor designs, which change the extent and spread of fire. On the exterior wall of the building, they look very different from what we had a few decades ago. You have different air tightness. Your windows are typically have a lot more integrity. You might have some combustible materials within the construction of your exterior wall. And then the system is a lot more complex. That facade has to provide lighting, energy performance, fire safety, constructability, aesthetics, all of the above. And so there are competing demands from the exterior wall, which means we have much more complex systems to deal with compared to, again, 50 years ago. We also have new building materials that are becoming more common, high performance concrete, heavy timber, etc., that are coming into the structures, but we don't really treat them separately to see what that means for the design. Looking at firefighting response, obviously, if you have a taller or larger structure, it takes longer and it's harder to have access for firefighting, right? That should have an impact on how we look at these designs. It's harder to evacuate a taller building. It might take too much time for you to do that. And then during this time period, the fire loads inside the buildings have changed. The composition of how we build the sofas and the building materials and the construction type, all of those things have changed. And we also have new changes that are coming up. So for example, we will have a lot more electric cars driving into the buildings, right? They have lithium-ion batteries, which is a different technology, but the fire from a lithium-ion battery is entirely different from a fire that you get from the contents of the building. That's a different profile of fire that has to be looked at. We will have a lot of lithium-ion batteries as energy storage system. That's the dominant technology in energy storage. So again, it's a different fire risk. We need to understand what that means for the building. And I went through a long list of things that have changed over time. These changes have had reasons for them. They do serve functions. So I'm not talking about turning back these changes, and it's not necessarily wise to turn back any of these changes. We have different buildings, but we have to design accordingly. So now, when you look at it from a firefighting perspective, there are a few things that will have an impact on your decisions. One of them is obviously building stability. So here the question is, how long will the building stand up, and for what size of a fire? If you have failures, will they be local and contained failures, or will they be global failures? Will you have advanced warning that something is going to give way? And how long will you have before that collapse? So these are questions that are very related to the design, right? But they really impact firefighting decisions. And the nature of fire itself. Is the fire local, or does it involve the entire floor? What is the speed of that spread? Are there any additional specific hazards, such as hazardous materials or explosion risk associated with it? Has the fire spread to multiple floors? Is there fire on the exterior of the building? These are very impactful on how to fight the fire. They're all driven by design and construction of the building. There's also the question of search and rescue and whether you can evacuate or have to evacuate, or whether people can shelter in place safely. So obviously you need to know how many people are in the building and where, but then the question is sheltering in place safe? Can the building stand until the fire burns out? Does the fire service have the resources, and does the building provide the right infrastructure to allow for containing or extinguishing a large fire? And related to all that, are means of egress adequate for timely evacuation of the entire building? Or do you have to have shelter in place as part of the process? Again, these are questions that are impacted by design and construction of building. On the logistics of fighting a fire, how long does it take before you can start the effective firefighting? If you're fighting a fire on the 40th floor of a tall building, you can't just go in, right? And you don't have access from ground level to help you. How much does search and rescue interfere with the firefighting mission, right? Those are competing demands on the same people and on the same means of egress, for example. And are the building fire protection systems, such as the standpipes, the sprinklers, are they adequate for the type of fire that you will get in that building? Or are they helpful, but they're not enough? And then how typical is the fire? So if you're dealing with a fire that happens frequently, you've had experience with this, your colleagues have had experience, that's useful, right? We know how to fight them, they're known. So that's good to know. But if you have a large fire in a complex and unique building, such as a high-rise or a complex space, we probably haven't experienced many such fires, right? And so each of those will be a unique experience, and so that bears on the decision-making by firefighters. And to the extent that we've thought about this or we haven't, are those things that have been or can be captured as part of the training, so that even though you don't face that fire every day, when you go there, you've gone through the exercises multiple times, understanding what will happen in the building. So these are all very relevant questions to firefighting: building stability, the nature of the fire, search and rescue, logistics, and the nature of the fire, how typical is that? Most of these are impacted by how we design the building. And so that relationship is very important. For most of the buildings, if you ask these questions, we don't know the answer. Not that we can't know the answer, but we don't know the answer because we haven't analyzed the building, that the design process does not require such analysis. And so that is a limitation, right? You don't have the answer to the relevant questions to make the right decisions for your safety and the safety of the people. So although the design doesn't answer these questions, the design and construction determine the answer to these questions. We just don't know them because we haven't asked the question. So to me, that is a real problem, right? That does pose real risk to firefighters and the public. And the solution, the key to the solution is knowledge. We need to know what we have. For a specific building, what are the risks involved in the fire, the building stability, the egress and evacuation, and how do those things interact with each other? What are the consequences of your fire, right? And what are those interactions? We also have to realize that for these more complex buildings, each of them is a custom design. Each of them will have a somewhat of a different behavior. Going back to my previous analogy, each building would be a different shuttle. You can't just copy paste and assume that it's safe. You really have to look at the specifics of your building. And so the solution to that is performance-based design. That's a term that you might or might not have heard, but what it really means is you're looking at individualized design for acceptable consequences. So you're looking at your building, the one building, as opposed to a typical building, whatever is specific to that building. And you're looking at the consequence of the hazard, right? In this case, for a fire, what will happen after the fire? And what you're trying to get through your design is to make sure that those consequences are acceptable. Those are consequences that in this context you can literally live with, right? That's performance-based design. And that is a rational design process. So you have very specific safety goals, and everything that you do is because it's providing some additional benefit in terms of getting to that goal. Now, I mentioned before this, I'm describing the process for new design, but even if you have an existing building, you can use the same process to understand your risks, right? Your hands might be more tied into changing what the building is, right? If in new design, you can actually change that in existing building, it is what it is, but you could still analyze and understand what the risks are, what the implications are, and that could inform how we would tackle firefighting in such buildings. Now, I mentioned this as a problem. I think I gave to why this is a problem, but this is also not just a theoretical, abstract problem. This is a recognized problem. I'll give you a couple of examples. Here are a few examples from full-scale tests that were done by NIST very recently. So they did a couple of tests on steel beams, long-span steel beams with concrete on metal deck. So very robust construction, fireproofed fully, and they subjected them to realistic compartment fires, which are typically less intense than the furnace test, what we use for fire resistant testing, right? So the fire was realistic and less demanding than the testing. In their testing, they had several cases where the beam failed. So you would have a collapse of the beam that's fireproofed, and the failures happened in the range of, an hour plus minus in some cases. The failures happened, some of them during the heating, some of the failures happened during the cooling phase. So they had cases where they turned off the furnace, they're going home, and the next morning when they come in, the beam has collapsed, right? And you can see the behavior of, again, these are code compliant, perfect construction. This is how the beam looks like. Obviously, they've removed the fireproofing so you could see what it looks like. You have failure of the connections. You have separation of the concrete from the metal deck. The bolts have shared off, major failures in designs that are realistic. This is another test where they did a full bay, two-story full bay, actually 2 bays of a building, same type of construction, and the testing was finished a few months ago. So for this one now, they're using the standard fire curve. So this is what you would use for getting your fire resistance rating. And this is constructed according to a 2-hour rated construction. And after 70 minutes, you have major breach into the slab. So you're having flames showing up at the next level, which means now you have a fire that has engulfed 2 floors. Entirely changes everything about assumptions of stability, evacuations, and how you fight the fire, right? And that happened in 70 minutes for a structure that is fireproofed for 2-hour fire rating. At 70 minutes, they stopped the testing, so they did not continue, and there was no collapse because of that yet, but there were major damage, including rupture of some of the bolts at that point. So this is not a theoretical conversation. These vulnerabilities are real. And these are very substantial structures, right? These are robust buildings. A lot of the buildings are not as robust as that. Similarly, there was a study that was sponsored by ASCE, which is the American Society of Civil Engineers. We were part of that discussion, and we looked at 4 different buildings and how a prescriptive design would behave in fire versus how a performance-based design would behave in fire. And for example, we looked at a typical high-rise and a comparison. And in the case that we studied, Because you could not evacuate that building quickly, the goal was getting resistance for full burnout. And there was no amount of fireproofing that we could put for that specific design that would get you to that performance. A safe design did require adjustments to the structure, most notably to the connections, and also some redistribution of the fireproofing. And actually, we put more fireproofing on the connection, we put less fireproofing on the beams. All in all, there was less proofing within the structure, but it was distributed such that it's where it's providing the most benefits, and the structural connections were also adjusted to provide that performance. So we managed to show that the prescriptive design is limited, but B, you could actually provide a safe design, and that safe design is not necessarily more costly. It's just you've gone through the process. I also want to bring a quote to say this is also not just structural engineers talking about this. So this is a quote from Bobby Halton, which I'm sure Glenn knows him very well. He's the editor-in-chief of Fire Engineering, and he's the education director of Fire Department Instructors Conference. And he was chief of training and operations at different times at Albuquerque. This is from a paper that was published probably less than a month ago. I'm just going to read the quote. While the fire service is thoroughly engaged in evaluating our tactical and procedural approach to structural firefighting, the very battlefield where we conduct those firefights is not undergoing the same rigorous evaluation and study. American firefighters want buildings and their structural systems to be studied under modern fuel loads. We want these structural systems tested as a complete building, not individual pieces. We want that research communicated to us so that we can better evaluate areas of refuge and evacuation routes and have a greater sense of understanding regarding collapse and failure. So this is a real problem. We have real solutions to that. And so we want to see what the implications are. I'm bringing another quote also from Dr. James Quintiere. For anyone who might not know him, he was the chief of fire science and engineering at NIST, and then he went to University of Maryland and was a chaired professor at the Department of Fire Protection Engineering there. They asked him about one area where you would want to do really more studies. And he said, we have spent 50 years looking at the way the fire starts at a room, rather than once the room is fully involved, how does it affect the structure? So this is a very relevant question for us. Now, my background is structural engineering. So my focus has been more on building stability as opposed to, for example, the standpipe capacity. But I do want to mention that the other elements of fire safety, meaning means of egress, and also the design of sprinklers and standpipes and smoke control, those are also prescriptive, right? So the design doesn't say, okay, you have a large floor, it's an open floor, you're very likely to get a fire that involves the entire floor. What is the water that you need to fight that fire successfully? That would be a performance-based design, but the design doesn't do that, at least at this point. And so I've talked about limitations of prescriptive design, but very broadly speaking, the main limitation is that you have unknown and in many cases unacceptable fire consequences. But the fact is it's unknown, so you can't plan accordingly to know how to provide safety. It's also not the most effective use of fire safety measures in a building. It's not a rational design. You're not doing things because they provide a benefit. You're doing things because you are checking the box in the code. All in all, the combination provides some benefits, but it's not the most optimal, the most rational design. And so that actually could mean that you have a more expensive design. It's not providing as much safety at the same time. Now, let me spend a few more minutes talking about why we get all these limitations from prescriptive design, and then I will jump into the discussion of implications. Really, one of the main problems is that prescriptive design is based on component tests, not system tests. So we test an individual beam or an individual column. We don't test them together, and then we don't analyze them together. To bring the point home, we don't even test connections. The whole process does not have a protocol on how to test a connection. And I've mentioned connections are one of the most critical elements of building stability in a fire. So that's just not part of the process. The process does not look at the effect of thermal stresses properly. It doesn't look at what happens during cooling, which is where you might get failure. And again, cooling is relevant to firefighting. If you're fighting a long fire, you will be there for some duration after, or you might be in some part of the building, and in another part of the building, you are going into that cooling phase, right? This is a very relevant question to life safety. Even going to the question of whether you can evacuate safely, that's a question that's not asked in the code. The code gives you prescribed means of egress, but very simple analysis can show that in many typical layouts, you could actually lose people, significant number of people in a building that is code compliant, because we don't ask the question. Once they check the boxes, the design is considered acceptable. Also, the design process does not tell you whether the building is safe to go inside after the fire, because we don't quantify the performance. And again, that's very relevant if you are a firefighter going into the building at that stage. And when it comes to the fire itself, we're always testing to the same fire. It's that black curve in this plot on the right, top right side. We don't look at what's in the building. We don't look at the geometry of the building. The fire could be hotter or colder. It could be shorter or longer. The design process doesn't care. It's always that black line. In a lot of buildings, the actual fire demand on structures could be a lot less. We don't look at that. In some buildings, the demand might be more or different. Just to bring an example, I mentioned lithium-ion batteries. If you have lithium-ion batteries having thermal runaway and starting to catch fire, what they produce is a much hotter fire. The temperature of fire is more than the melting temperature of steel. So that's different from what we're testing for. It's also initially a much more intense fire, and it produces its own oxygen. It's much harder to fight. And the gases that it's producing are also potentially explosive. So it's harder to get close and deal with that. All of this means that it's a different fire risk. It doesn't mean that you can't deal with this, but it means that you have to deal with it, right? If your process hasn't looked at that, then you have an unknown risk to everyone. And an important question is, if something fails per design, because the design is not always trying to prevent failure, right? Even the code, it gives you specific durations of rating. The presumption is, if you have 2-hour rating, I think everyone assumes that that means you have 2 hours of stability. That doesn't really mean that, but it could be for a limited time. But what is the consequence of a failure? A failure of a building that's smaller, where people have gotten out, where the failure is contained, is very different from a failure of a larger building where people will be inside and you could also have an impact on the entire neighborhood, right? We could presumably deal with those designs in a different manner. And the bottom line is, in the standard design process, we don't design explicitly for safety. We presume safety. This is an interesting video. This is a building in Netherlands. It's a concrete building, which you would think of as somewhat more robust. And they had a small fire starting from a coffee vending machine. And you give it enough time, and it brought down a significant portion of this concrete building, right? That could happen because, again, we don't design for safety in fire in that sense. We don't explicitly design for building stability. So I think we do need to move toward performance-based design to have a right solution for that kind of a building. And what that means is individualized design. You look at that specific building and you are explicitly designing for acceptable consequences. That's the only way to verify safety and plan accordingly. Otherwise, code does provide measures that mitigate risk. You know you have some risk mitigation because of all the things that go in, but you don't know how much mitigation and what is the risk that you are dealing with this. I also want to highlight again, I'm not saying that this is the answer for all the buildings. A lot of the buildings are common enough within the range of where we've seen many, many fires and we know what to expect. This is really for designs that are outside that range and have high consequences. So we want to define performance goals and have them drive the design. So some of the relevant questions here are, what are the access, protection, and time requirements to evacuate or shelter in place safely? This is for the people inside. And to fight the fire safely and effectively, right? Those are relevant questions. Those things should drive the design on access, protection, and the time that the structure gives you to do those things. Fire protection measures and systems, means of egress, all of them should reflect that. The structural design should also reflect that and provide adequate stability for that duration. Or in principle, you could design buildings, high impact buildings, for full burnout, where within each area, the fire has burned out and the structure can stand up. If you have a bad case and the fire is traveling, you might have a fire that extends for a long duration, but within each limited area, the fire burns for a limited duration before it dies out, and you can design the structure to be stable for that duration. The bottom line is firefighting strategy and design should be consistent. They do relate to each other. They have to also talk to each other. Now, I've talked about performance-based design. It's important to note that codes do permit performance-based design. This sentence at the beginning, that's the first sentence in the introduction to IBC. It establishes minimum requirements for buildings using prescriptive and performance-related provisions. So the process is permitted. Providing life safety for firefighters is also an explicit intent of IBC. And I mentioned IBC here as the mother code, where almost all the other codes are directly or indirectly taking provisions from IBC. So just for the sake of discussion, most codes would have the same types of provisions. And the code also allows for alternative materials, designs, and methods, but they just have to be approved by the building official or the authority having jurisdiction. So this is a process that's in principle permitted, but it does need specific approval from the authority having jurisdiction or the AHJ. We also have standards for performance-based design. We have standards within the steel manual, within concrete documents, within heavy timber documents, and there are codes in how to do that. So ASC 7, which is the document that tells us how to design buildings, in ASC 7 2016, Appendix E has an appendix that explicitly discusses structural fire engineering. ASC followed that with a manual of practice and then a practical guide to engineers on how to do that. And we helped on authoring this last document. So it's there, it's permitted by the code. It's also safe and has precedent. And it's good to look at it more broadly. We're talking about fire here, but obviously we design buildings for other hazards that could also be significant. For example, earthquake risk is a major driver in a lot of areas. We've been using seismic performance-based design for at least 40 years now. We're doing it widespread. If a building is important right now, most of those buildings do get through a performance-based design process as opposed to a prescriptive process. As an example, I want to mention, whenever there's a design for terrorism, most of those designs are actually performance-based, meaning you really identify what the risk is, the realistic risk, and you identify what is the acceptable consequences. And these are not great consequences. You have damage, but they're acceptable consequences. What is the damage that you can live with so that you can protect life, right? And you run the analysis or the testing to make sure that you get there. So that's a performance-based design process. And so ASC, which is the engineering community for us, is advocating performance-based design for all hazards. They just released within the last year new guidelines for fire and wind in the context of performance-based design. So we are within the context of what the design community is trying to do. I also want to mention that fire is quite unique here. When we talk about earthquakes, for example, we run numbers. There might be simplifications in design, even in prescriptive design, but prescriptive design involves a lot of actual engineering, whereas prescriptive design for structural fire involves zero engineering. So when we're talking about performance-based design, we're talking about going from doing nothing to doing analysis, right? It is an important step. And I also just want to mention, we don't have time to go through a lot of examples, but fire performance-based design has also been implemented within the US and globally. So it's something that we know how to do. It's just a harder process to get through, and not everyone has been doing that. Now let's look at some of the implications. So one of the questions is, why would a public or private owner want to do fire performance-based design on their project, or decide not to do that? So let's look at it from that perspective, because we need to understand construction industry as a whole if we want to have more performance-based design. So the important points here are, one is performance-based design is optional. It's not mandated by the code. And also not many projects need it. Not all projects need it. A lot of projects don't need to go there, right? Performance-based design is also an intelligent design. It's a rational design. So typically what that means is that for the same level of performance, for the same safety, you actually get a more optimal design. And so in a lot of cases, what you can get is you can manage to improve safety, reliability of the building, and at the same time improve your design flexibility and economy. So in that sense, it would be an attractive option for an owner. Some owners might care about all of the above. Some owners might care more about the design flexibility and economy aspect of it, right? But that package does have the improved safety and reliability. You can't get the financial benefits if there are some without getting the safety benefits. And so that's important to note here. But we also have owners and developers that actually really care about that safety provision. It's the building that they're going to go in, and they do a lot of things to make sure that they attract the best people and they provide a safe environment, and they're model. So they do care about that too. But even for clients that care, I think the biggest question mark for owners when they want to decide whether to pursue performance-based design or not is the approval risk. If they think that that process is going to be just sidetrack the entire design, they might decide not to pursue that, even if it has the safety and financial and design flexibility and reliability risk. So that's really the biggest deterrent on the developer and owner side. I think it's also really important to look at this question from an AHJ perspective. I'm not an AHJ, but I can say this. If I were, these are the questions that I would be looking at. It's really important to emphasize that the burden of proof should be on the design team, and it is on the design team. So the design team is coming and asking to do something different. The AHJ has to be very probing and make sure to put them to the fire and make sure that they actually provide a design that does provide all of that. When it comes to the context of fire, it's important to note here that structural analysis should be part of that process. If there's a performance-based design and it doesn't look at how the building behaves in a fire through an actual structural analysis, that performance-based design is incomplete. I think third-party peer reviews are also an important part of this process. They're important because they allow you to ensure the quality of the process, to make sure that There's a design that's more complex. It's more advanced. You want to have a second person, a third person that has no incentive in the project, has the right qualifications, and have them vet the process too, so that there's more confidence and assurance to the AHJ. So I think those 3 steps are really important to ensure that performance-based design is done in a manner that provides the promise, provides safety for the building. I think it's also important to note that the alternative to performance-based design is not a safe design. The alternative is a prescriptive design. And those are 2 different things. The assumption should not be that if we don't go through that process and the prescriptive design is used, we're good. We know that these buildings that are prescriptive do have vulnerabilities as well, right? So that's good to keep in mind. And if a design really does produce a safer design, but it ends up being less costly, that is fine. That's a good thing, right? That actually makes sure that the incentives are there. The final result is we will have more buildings that are designed using this process. So we will have more buildings that are safe for the people inside of them and for the firefighters. So I think both sides of that are important to have in mind. It's really important to do the first 3 things to make sure that the quality is there. It's also good to remember that the alternative is not necessarily safer. I think a question that is relevant, I'm not sure if anyone is asking the question, but should performance-based design be mandated for any structure? To me, the answer is maybe. It does involve more things. It does really depend on the context. So the real question is, what are the consequences of a failure? If you have high impact buildings, especially in dense urban areas where a failure could have very catastrophic and large scale unpredictable consequences, looking at resilient designs as a whole is a good idea. This would be a change, right? And I'm not just talking about fire in this context. If you're putting a very substantial building in the middle of a very dense urban area, you want to make sure that that design is resilient for seismic forces, for fire forces, if it's relevant for terrorism, if it's relevant for flood, right? Having a process to look at resiliency more explicitly and then decide whether there is something more that has to be done for a specific building is, I think, a good idea that each local jurisdiction should look at and decide whether that's relevant to them. I do want to mention one point here, though. Obviously, any times that you do something that increases the cost, there will be pushback to see if it's justified. I want to highlight the point that performance-based design is a rational design. For the same level of safety, you get lower costs. So putting it in a different way, if you're spending the same amount of money, you can always improve safety, right? So if done right, in most contexts, performance-based design is not a more expensive design. It's just a more rigorous design. And that's something good to have in mind. Resilience doesn't mean more expensive. It just means better. Now, design can definitely make firefighting safer and more effective. I want to go through just an example, very high level. Let's say you're looking at a high-rise. Depending on what you have, timely evacuation of all the occupants might not be viable. And it's a high-rise, so it takes more time to start your effective firefighting. And just for clarifying here, for high-rise, I don't mean more than 75 feet. I mean, tens of stories in this context. In these buildings, it's also very common to have open floor designs, and that allows for faster spread of the fire to the entire floor, right? So it might be very possible for, if you're responding to a fire in a building like that was not initially contained by the sprinklers, that you will have a fire that's engulfing an entire floor. And so the design of sprinklers or the design of standpipes does not necessarily incorporate that. They're not necessarily designed to fight a fire that's involving the entire floor roughly at the same time. That's something that in the context of fire protection engineering can be looked at, right? That's an element of design. On the structural side, design for fire burnouts would certainly be more resilient in this context because it does allow firefighters to safely address the fire without having to choose between their own lives and the lives of the people on the inside. It's that time pressure that is really key to increasing the danger to everyone. If you know that your building is safe for the fire that you have, that as long as you've evacuated people from the immediate vicinity of the fire, that the building will stand up, people can stay within the building safely, that's a much easier firefighting job. And it doesn't require you to put your lives or the lives of people in that balance and trying to make a decision, right? So certainly design can provide for better, safer environment for people and firefighters. Let's talk about existing buildings a little bit. My discussion talks about design, and again, sometimes you would think of that as new design, but the same discussion really does apply to existing buildings. And going back to my main point, the key is knowledge. If you have knowledge of what to expect, that allows you to have safe operations. If you have prior knowledge of what to expect, that also allows you to actually plan for it and train for it and have your operations really reflect that, so you don't have to make decisions in the field where you have all the different types of pressures. And so we can certainly study specific high impact buildings and see what to expect from them. Or we could study a group of high impact buildings and see what are the common features of them and use that to provide guidelines regarding what is the safe way of dealing with fires in such buildings so that the people and the firefighters are safe. And so for that, we need to quantify the answer to these questions. What are the reasonable and realistic fire scenarios that could happen in those buildings? What is the structural response to the fire in that scenario? And how long is it safe how long is the structure safe in that fire? What are the realistic evacuation times and limitations? And what can the firefighters do with the available standpipes, sprinklers, and so on? What does the infrastructure of the building allow in terms of firefighting? If you have the answer to those 4 questions, then you can come up with a plan that's targeted to that building or that type of building, and it's more effective and safer for everyone. If this study is also done ahead of time, which is the idea here, then operations and training can be adjusted to reflect these findings, right? We have time to really go through the exercises, come up with different ways of approaching the fire, test them out, think through them, and come up with a plan that works better for everyone. And in principle, if that is done, you could have that guidance available at each building. There's a fire, you go in, there's the fire command center. Part of the information that you have is, this is what's relevant to this building. This building, we expect it to stand up for 75 minutes if you have a fully engulfed fire. That's an information that you could use to make decisions. In this building, we think if all the stairs are available, you can evacuate people in 45 minutes, or it's going to take 3 hours to evacuate people. Those lead to different decisions as a firefighter. And those are the type of things that, in principle, we can do for existing buildings. For new buildings, it's all the same thing. The only thing is we could actually do something about it on the design stage too, so that that battlefield is a more favorable battlefield. You have more options, you have better tools and better decisions to make. So I think I've talked quite a lot about things that have relevance to firefighting, but let's talk about what as a wrap up, what fire departments can do in this regard. And some of this could be short term, some of these are long term, and I'm really looking forward to feedback and thoughts from the audience. What do you think about these topics? there's certainly some advocacy for things that are going to lead to better safety for firefighters. I think explicit consideration of structural stability during fire is really important, especially for high impact buildings. I think that's in the interest of everyone, most of all firefighters. I think analyzing specific or typical existing high impact buildings could lead to information that leads to better operation manuals and better training for firefighters. It makes their lives better and safer. That's good. I think bringing the building response to the discussion of fire safety anytime that that's involved, but an explicit discussion of the building response, not just a prescriptive discussion, I think that would be really good. And the fire departments are in a good position to have these conversations. Building response to a fire really impacts firefighters. You're putting your lives at risk. You want to make sure that you have what allows for the best, safest environment. I think there's also a lot of research that can be done, and there's really a lot of money rightfully being spent every year on what to do to improve firefighter safety. Some of that money goes into equipment, some of that money goes into research. I think the questions that we've talked about today are relevant to firefighter safety, extremely relevant. So they have to be put as part of that research agenda. How to design buildings for resilience in fire, especially for high impact buildings. Some of that research should be focused on that. Once we understand those things, and to the extent that we do, how do we translate that into operation guidance for the fire departments? Some money and time should be spent on researching that topic and connecting these two things, translating one into the other one. Structural performance of existing buildings is a subset of that research. I think that's a really important topic to focus on. And I'm sure there are a lot more that you have on your mind in this context that I look forward to hear about. What else could be relevant in this context where research could advocate safety of firefighters. There's also things that could be done on training. Certainly operations for high impact buildings can be updated based on a knowledge that's specific and quantified based on building response in the fire and evacuation. Those two things will drive these decisions by the firefighters. And if we look at the answers there, we could update operations for these buildings. Certainly that could allow for customized trainings for specific high impact buildings. I'm not saying that this has to be done for every building, that we have necessarily the resources to do that. But it could be types of buildings. We have a lot of, again, high rises throughout the country, right? Any lessons learned can be studied and even exercised on some of these buildings just to see how that works out. There's room for desktop training. I'm envision flight simulators where you're a pilot, you go and you fly a lot of times, not in a real airplane, but in different scenarios, and you test out what to do and what the impact is. Something along that line could be helpful if it's tied to engineering and science, right? So if you have different building types and you model different realistic fires and you model the response of the building and you model the behavior of people, and then you make different decisions as a firefighter and see what happens, what are the consequences. Something like that could be very valuable. It could be visual, it could be not visual, right? But that thought, I think there's a lot we could do to learn when we're not in the field, because when you are in the field, you want to go through those 100 examples that you've seen, plus the one example or two examples that you have to deal with in real life. Hopefully these are rare events. We don't get a lot of practical exercise. We want to do all the preparation ahead of time. And another topic, another concept could be, you could even do institute training and exercises for high impact buildings. We've actually had some discussions on this with FDNY. You could use technology such as augmented reality or other things tied into the science that we have and go to a specific building and have an exercise and deal with a hazard without interrupting the operations of the building, without having any other cost, without having an actual safety risk, right? So there's a lot that can be done in training. These are my initial thoughts. Again, I'm sure there's a lot more thoughts within the audience. So to wrap this up, safe and effective firefighting is tied to building design. They do talk to each other. They do impact each other. And so we want to make sure that that discussion happens explicitly. Prescriptive code requirements have done a really good job of reducing fire risk for typical buildings. And that's important to acknowledge. They are part of the puzzle, part of the solution for a lot of buildings. And so I'm not trying to undermine that or question that. But they do leave something to be desired when it comes to events that are less likely, but more consequential, those rare events. And that's where performance-based design could really allow for improving safety for everyone, including firefighters. I also want to highlight again, this is a code prescribed process. It is recognized by the code, but getting it through has been typically more challenging. Part of that is understanding what you get, what to do to make sure that that design is actually safe, but also understanding that the alternative is not necessarily safer. It's just what we've done for a long time. And the last point is the same concepts can be used to improve operations and training for existing building. This discussion is not just for new building. With that, I'm really grateful for this opportunity from John Jay, and I look forward to comments and discussions and suggestions from the audience.
Okay, well, thank you so much, Ali, for a wonderful presentation. This really hit home, I think, for everyone who's on this Zoom session right now. We are, as I said earlier, I think we really are in a moment in time now where we're in a fork in the road, and really we need to take the new road to what you've outlined for us here today. Doing things based upon 100-year-old tests are totally inappropriate. Can you imagine if we did this for cars and for airplanes and for drugs and everything else? We use 100-year-old tests. So it's ironic that, of course, NIST actually did which of course back then was called National Bureau of Standards. They actually did auto tests back 100 years ago, but they're not in that business anymore because they realized, of course, that technology moved ahead and they wanted to focus on other things. So this is, again, an incredibly important topic for all of us, both in the structural engineering field as well as the fire protection field. I just got a couple of comments. Back in the day, I recall back in actually 1993 was one of the first conferences on performance-based design with regard to fire protection. It was actually up at Worcester Polytech when I was a graduate student up there. And I remember talking to a lot of folks and sort of talking with respect to the issues of prescriptive codes, which of course dominate everything even to this day, what we do. Prescriptive codes, of course, are a crutch to a lot of architects. They're an easy way to sort of deal with the issues at hand, basically. And so going to a performance-based code, of course, or performance-based requirements would certainly open up the doors for a lot more freedom, but it's not just the freedom of design, it's also that responsibility to actually tie it to some specificity in terms of what and how that building is going to perform, basically. So I think since 1993, we've come a long way. I think we now understand that we don't throw that word performance around lightly. It's something that we have to really take a good look at and understand. It doesn't mean you can do whatever the heck you want to do. Because I'm a former code guy for 10 years spent in code enforcement in San Antonio, Austin. And believe me, I saw a lot of bad performance-based designs, okay? And so I think we've come a long way since then. But at this moment in time, at this very, here in 2021, we literally have the very first specific provision in the International Building Code, which ties structural design, structural engineering to fire protection. It's coming up for a vote. And it's like I said, I think 20 years from now, we're going to look back and say this was a moment where we really tried to dismantle the archaic ways of doing things, which is basically shooting in the dark and trying to assume that, you know, things are going to be okay. When in fact, that's not the case, of course. We're extending now the same old tests into new technologies and new techniques and new materials and things. And we don't recognize the real shortcomings of a lot of these, again, archaic methods, particularly ASTM E119, the fire furnace test. You know, I guess from a fire service perspective, Ali, I see there's some firefighters on here. Mark Chubb is on here. Jerry Tracy's on here. A few others I see. You know, the fire service has never lived in a world where we had any kind of real, again, specificity in terms of how long a building is going to last, in terms of collapse potential. We've never had that. It's always been education, experience, training, and seat of the pants. Jerry Tracy, the former chief officer in FDNY, can certainly attest to that. He's out in the street looking at a building that's out on fire and trying to balance the fire attack with whether or not the building's going to come down while they're trying to do that. So this is like a remarkable thing to think about, that we've been doing it this way for so long. It's like, duh, we should be really looking at the building. We should be asking questions about how long we should expect things to last. And again, to have a much more closer look at the behavior of specific designs and specific materials. So anyway, Ali, I congratulate you on this. Like I said, this is, I see it as a starting point for all of us. And again, as I pointed out earlier, I think there is definitely a natural alliance between us, meaning the fire service, and the structural engineering community, that we both have a lot of similar interests and desires, and we need to move forward with this. Because one thing Ali didn't mention during his presentation is that unfortunately, this is a wonderful thing we want to do, but there are groups and folks out there who may not be as impressed with what we heard today and maybe not want to move in that direction for a variety of reasons. So I think, again, this alliance between the fire service and structural engineers is incredibly important. So let me throw out a few, Ali, let me give you a few comments and questions here. First one's from Mark Chubb. How do we, structural and fire safety engineers, overcome the presumption that more predictable structural performance in a fire must also mean better performance in a fire compared to assumptions about existing construction, i.e., resistance to higher heat release rates, total burnout, things like that. So, so how do we get over that presumption that we can predict better, but also, again, also means better performance in an actual fire compared to existing kinds of construction, things like that?
I'm not sure if I understand the question correctly. I think the question is asking what is the presumption that the prescriptive design is safe. How is this in any way safer, right?
Yeah.
And I think that is a presumption. I really agree with that. Like, people think about prescriptive design. Okay, I'm starting from a safe place. Now I want to do something different, and why would I even go there? Whereas it's just, we know enough. Like, once you start looking at it, we know enough about the process and about experience. We've seen this. I showed you examples, and those are not made up examples from the testing at NIST, for example. That's the best case scenario. Those are perfect construction. Those are very robust structures, right? And we know that the failures happen, and something could happen very early on. Just to me, the crux of it is we're not doing any analysis, period, right? There is no analysis regarding structural fire engineering in prescriptive design. And if you have a beam, or if you have a column, if you have a beam, the same beam, depending on how it's connected to the structure and what that structure is, will have a very different behavior that is not seen in the testing. It's just not there. The connections are a lot of times the element that fails. The connections are not tested. There is nothing to test. If you want to go test a connection, it's not there. You can't get a rating for a connection, right? That's that's a big flaw. So not as soon as you start looking at it, you see the flaws in the prescriptive process. It's just, it has been convenient. There's 100-year history of we've done it that way, and so I think that it's inertia.
Right, and I would extend that point a little bit, Ali, and point out that one of the arguments that we hear from, let's say, the prescriptive side of the audience is that it's done so well for 100 years. Why are we changing it? And of course, one of the holes in the argument is that we don't study actual fires in actual buildings. We don't do that. I mean, certainly from a structural standpoint, and we actually haven't done even from a firefighting standpoint, realistically, nationally for decades now. Ironically, Ali, you're probably not aware of this, but two of the authors of the fire report from the U.S. Fire Administration on the One Meridian Plaza fire in Philadelphia are on this call. It's Mark Chubb and, of course, Charles Jennings were two of the three authors on that. There was a time in our history where in the U.S. we actually studied large fires and particularly target buildings that we've been talking about here, but we don't do that anymore. So, there's a lot of failures out there. We just simply don't document. Right. And that's, again, we can agree that the the prescriptive codes have done perhaps good things for us for years, but we're at a moment in time again where we really need to shift to something much better and again, something more realistic. Let me and
I want to add one thing. That's a really good point. Again, I'm not trying to say that performance-based prescriptive design doesn't have its place. A lot of buildings are frequent enough, typical enough, where you could look at the data and say it's done its job. We have the record, right? It's when it comes to these high-impact buildings, which are now unique things. Each of them is, again, like a different shuttle, like a different car. They have different designs, they behave differently, right? And we've done enough things that mitigate the risk. So the performance of building comes in when the sprinkler doesn't do its job. Most of the time, it does its job and it's great. So because of that, we're not getting as many experiments. We're not actually building enough data where you could say, statistically, I've looked at it, the risk is low. No, like we have reduced the probability of fire, and that's great, right? Having sprinklers in a building is absolutely the first line of defense. You have to have that. It reduces the risk broadly. The question is what happens after that. In a tall building where typically we respond, we're trying to deal with infrequent but very high consequence things. We had a 9/11. We don't want to have a second 9/11. 9/11 had a component that was terrorism, but you could have a building that comes down without that aspect just because of fire, right? You don't want to be in that position where you're not talking about the loss of life of 1, 2, 3 people, but tens of people, hundreds of people.
Right. I've got a question here from Luke Rudkoskas. Hopefully, I probably butchered your name, Lucas. I'm sorry. As the structural designs are becoming more optimized, the factor of safety is becoming reduced in buildings that are designed with prescriptive fire rules. And these rules have not been changing too much. Do you think that might drive a wider use of performance-based design? So I guess what Lucas is saying here is that as you know, Ali, over decades, we'll say safety factors in general are getting thinner. Certainly materials are getting lighter and thinner, and we're sort of still using the same criteria. So to ask his question is, do you think that might be a driver for the wider use of performance-based design, given the fact that the safety is a factor actually going down, not up right now?
It's certainly the question to ask, right? Meaning a building that was built in 1910 is different from a building that's built in 1950, and it's different from a building that's built today. I think the changes in design have come for reasons, right? I do want to highlight this point here. More is not better. More expensive is not better. It doesn't mean that less is better or less expensive is better. You have to design for it. You have to engineer for it, right? If you engineer, you can design something that's safe, resilient, even higher level of safety, but you're using your resources also better. You're using it where it provides a benefit, not just randomly to improve benefit somehow, right? So in that context, we have buildings that are lighter. We have buildings that have different materials. We have buildings that have larger spans. The building technology today is what it is, right? So our job really is to make sure that we provide the safety for what we have, because there are reasons why the materials are different, the construction is different, the facades are different. They're all things that have changed. We just need to make sure that we do the right due diligence, we do the right analysis to make sure that that new design is still safe. I think you're on mute, Glenn.
Yeah, I'm sorry. I'm going to turn this over to Charles. As I said earlier, I have to go teach class. So again, Ali, thank you. And thank you for the wonderful turnout we had today for almost 50 attendees today to this lecture. So again, thank you to all you as well.
Thank you, Glenn.
Okay, so all right, let's keep going. We have a lot of questions here, Ali. So I'm going to go ahead and queue those up. And
I just want to say, I also take comments, right? If everyone has comments and not questions, that's also a very welcome feedback.
Okay, you heard that, everybody. And please don't be shy. You've got some great people on the call, so don't sit there with a question that you're too shy to ask. So this second one, and I'm going to just jump right in. Does Bobby Halton's editorial opinion say, in short, you want a building permit, great, build 2 identical buildings, set one of them on fire. If we like what we see, you get to keep one of them. How do we manage expectations of structural fire engineering and how we generate, use, and evaluate data from large-scale testing?
Okay, I think that's a great question. And it speaks to something that's really relevant. I'm going to use my analogy of the shuttle. So on one side, you could test very specific small components of the shuttle and say, I'm done. That's one end of the spectrum. That's closer to where we are in fire design. On the other hand, you might say, you know what, I need to take this, build it, assemble the whole thing, fly it 10 times, and then that's my testing. For something that's reusable, maybe, but for something that where the testing might destroy it, so it's like a one-time use, the next time that you build something, it will be somewhat different, right? And it's also a very expensive test. So what you do is you do enough testing to understand all the pieces. You do enough testing to understand some of the interactions at a larger scale. And then there's also heavy engineering to tie all of those things together, right? That's how we deal with seismic design. So when you're looking at a building, we test materials, we test connections, and we also run some fuller scale tests, but we don't build a 100-story building and test it in seismic. We can't do that. But we do build 2-story buildings and 4-story buildings and test them in fire. And we're not testing to get a rating. We're testing to increase our knowledge. That's the key, right? We're testing for understanding. Once you've done that and you've done the testing at a scale of at least a couple of stories, a couple of bays, that's information that you can then use in addition to analysis to now building something that's 20 stories, 50 stories. So I don't think Bobby Halton, I can't speak for Bobby Halton, but I don't think the suggestion is to build a 50-story building, set it on fire, and then build the next one. But the idea is, let's step away from just testing small pieces of the building. What NIST did, which was 2-story, 2 bays, that's not done commonly, right? So let's do a few more of those things, for example. That gives you information that you can extrapolate from. So I think that's a really good question. The answer is not something that's infeasible. With realistic testing, we can get a lot more information to improve safety in the design.
Okay. Kind of on this same line, I'm going to jump ahead here. We got a question on engineered timber. And that's a technology that's coming. A lot of people are a little uneasy with it, and they feel that the approvals are running ahead of our experience, and there still seem to be some fundamental questions. We did a pretty thorough look at this, I guess, a little over a year ago, and there were still issues on adhesives for laminated products and delamination and all that. So what's your thoughts on kind of the status of timber construction and where they fall in relation to, you talk about multi-scale or multi-story testing and failure of sprinklers, which is always, I think, the most important, even if not the most frequent, but an ultimate kind of test for the structural system.
Right. I think that's a really good question. And again, in this context, I want to look back to how I see it broadly. Sometimes there are changes that come and there are bigger drivers, right? So we need to understand what the implications are and determine what's safe or not, and then deal with that. There is a drive for mass timber from a sustainability perspective, and that drive is a significant push for it. So we do have to take the question seriously. To me, timber is another material. You could engineer it properly, but you have to engineer it properly. It does change the risk profile for a building, right? Now you are putting something as part of your structure that is combustible. That is different from when your building structure itself is not combustible. That has, if you are building structures of heavy timber, and if those buildings are again, more high consequence. If you're doing something that's a few stories, the current code allows that. The current code also allows, light wood construction, which is entirely different, right? So, but when we get to the range where the impact becomes really significant, I think performance-based design should absolutely be part of that process. You need to explicitly look at the material behavior. You need to explicitly look at how the fire interacts with timber. You have to explicitly look at what happens after the contents of the building have burned out, right? Because timber has properties that are actually better than steel. It also properties that are worse than steel. Timber has, so this is a broader discussion. I've had this discussion in other places. Steel and concrete have some very major vulnerabilities that timber doesn't have. They're very vulnerable to thermal expansion quickly, and that could cause damage. Concrete is very vulnerable to spalling, and once spalling happens and your rebar is gone, it's very vulnerable. Timber doesn't have any of those things. So it has good things going for it. The bad thing that it has going for it is that it's combustible, right? It's combustible in a way that's different from light wood construction. So light wood construction catches fire easily and it goes. Heavy timber, it actually needs a constant flow of heat for it to continue to burn. If you stop providing it heat, it will self-extinguish. That's a property of mass timber. But that's a question. If you have a building, you have something inside of it and the contents have burned, what does it take to ensure that the timber does not continue to burn, right? I think that's the key question to answer. If you can answer that question, which does involve testing and it does involve a lot of engineering, then you can have a safe design. If you don't address that question, then it becomes trickier. You're now in the range where you're trying to mitigate your risk. So I'm all for having sprinklers in these buildings. You do want to mitigate the risk, but sprinklers are the first line of defense. The structure on its own should have enough resilience. There is a way to design safe heavy timber buildings, but they have to be designed.
Okay, and any thoughts on the materials challenges in terms of, to the layperson? It's similar to the cladding issue. Right. You look at it, is this fire rated, is it not fire rated, what's its performance? Where are we with regard to that?
So I think there's decent testing on timber. We understand enough of its behavior. I would always advocate for more research. And there's more research being done, but I think there are certainly more things that we could be looking at for timber. There are also some more things that we could be looking at for steel structures, like substantial stuff. So when I look at them, I don't see as much of a substantial difference on the building material side. The risk is the fuel side of it. Timber is a good material, if you design it properly. It can self-extinguish if you design it properly. I think that's the question that needs to be answered. So to me, it goes back to that bigger question. You could design it prescriptively, and the prescriptive design does give you some fire rating. If you want to know actually what's going to happen, you do have to bring that science and engineering and look at the design. And I mentioned broadly and specifically for, if you're looking at taller mass timber, I absolutely advocate the AHJ has to be very probing. The burden of design is on the design team to show that what they're doing is safe. And I would encourage an AHJ looking at that to look at beyond the fire resistance terminology, looking at what actually happens in the fire and how will the building stand up. But with that, there is a way to design them safely. You just have to ask for it, and you have to make sure that that process is done. Timber, just as a historic notation, if you go back to the previous century, not 1900s, but 1800s, when they started to develop steel was losing its properties very easily in fire. Mass timber was standing up. You have these buildings where the steel elements have fallen down and the timber is there. They developed fireproofing for steel to raise its performance to the level of mass timber. It could be a good material, but you need to understand its weaknesses and design for them.
Okay, we've got a number of questions here, and I think they're already stacked up. We're not going to be able to get through all of them, so let me start doing some triage. And one of the points I wanted to make, or that you raised, and you know, having been around a while in the performance-based design business, is, you know, it's always out there in some degree. You know, it presumes there's going to be significant changes in the way AHJs operate, in the level of training and expertise. And ultimately, we had Jose Terrero in a couple of years ago who gave a really nice address for us. And basically, you know, threw the gauntlet down to say, if you're going to be practicing on these projects, you know, in the realm you deal with, right? Not the guy who's doing the, you know, we're going to do to renovate on the 20th floor of a 25-story building, but, you know, designing a novel project. Do we have enough skilled, certified personnel in the industry, in the engineering community, to really pull this off? When you factor in the challenge of third-party review and the issue of who's going to staff or advise the AHJs. And I know some of that is with third parties, but I think it's, you know, as it hasn't been an AHJ, you want the level of trust that you have somebody on your staff who you can say, you know, unequivocally that, yeah, they're okay with this, we're all right. So that's the question.
I think it's a great question. Obviously, to the extent that the AHJ has more resources and more technical resources, that's great, right? So absolutely, I would advocate for that, and that's a good thing. At the same time, I understand that everyone who is acting as an AHJ cannot be expert in everything at the same time. It's impossible, right? And even within a jurisdiction, especially smaller jurisdictions, you can't be experts on everything. So to some extent, that is the role of the peer reviewer, right? So that is why when we're doing performance-based design, it's doubly important to make sure that you do bring someone on board as a peer reviewer, that you look at their qualifications, that they do seem to know what they're talking about. They've talked about this, they've published on this. You could ask them your questions. I think you take any expert in any field. If you ask a few probing questions, you understand if they're deep in their field or not, right? So, and then with that, at some, I understand, I think I understand the perspective of an AHJ. It is a tough thing to be in a place and you're trying to approve all these things. I just want to say, again, the alternative is not necessarily safer. Having a third-party peer review the work, someone who is qualified, that's the right process to make sure that the best person goes and does that. The fact is, honestly, it's almost impossible for an AHJ to be the best expert in every field. It's impossible, right? That's an impossible thing to ask from an AHJ. The best thing is to bring the best people to act as your peer reviewer. And now you have confidence that the process is right. But be probing, be questioning, be skeptical. I think those are all good attitudes when you're looking at performance-based design, as long as you also understand that prescriptive design is not better. It's just the typical, it's the common solution.
Okay. Okay, some more recent questions we got here. One is, I think, the succinct. What do you think of the use of shelter in place as a strategy in unsprinklered, an existing high-rise building?
Well, the real answer is my expertise is not in that realm. So I am going to give you a sense, but someone should really deeply study that. I have deeply studied structural behavior in fire. I've looked at that question and its interaction with evacuation, but I'm not a fire protection engineer. I haven't designed sprinklers. Having said that, I think that's a firefighting question. To the extent I can add something to that, if your building is able to stand for the fire load for the duration, if you're not worried about structural collapse, and if you can get the right access, and if you have that scenario, this is a realistic scenario. You have people, they are in the building is on sprinklers, that's your set of facts. You could focus on protecting the building from the spread of the fire. You might not have the right resources to extinguish that fire, but that fire will die out at some point. But you probably have the right resources to make sure that the fire doesn't impact other people. But the presumption there is that the building is stable for the duration of a fully engulfed fire without intervention of the fire department. I think that is my concern. If you have that, everything else becomes easier. To give you an analogy, we've come a long way in seismic design. There used to be a time when the focus was on just making sure that the building does not collapse in an earthquake. We've come a long way now in a lot of the more higher impact buildings. Of course, that's a goal, but then the goal is to make sure that the building functionality is not impacted as much, that the non-structural damage is minimized. But all of that is only meaningful if you get the structural stability, right? So to me, that's the first question. In your building that's existing, not sprinklered, I would pose the question of if it's not stable, none of the strategies work. If it's stable, even if it's not sprinklered, but you know that it's stable, you will have a strategy to make sure that it doesn't affect the people inside.
Okay, all right, that was a wonderful answer. You dodged that ball quite well. So the next one here, this is another quick one, I think. Somebody's asking, what's the feasibility of having, and this I guess would be in really, you're making the analogy of a 100-story building, of having some kind of fire suppression capability resident inside the building. In terms of this is like a human resource based.
Again, I'm not the expert in that. I don't design sprinklers and standpipes. I think if you have a 100-story building and if you want to design it such that you have the right resources within the building, there would be a way to do that. It's cost and money, and you have to see what's the best use of the resources. Again, I'm not also advocating you just go and do things. We can add more demands if there's no tangible benefit associated with them, or if the cost is astronomical, it will not happen, right? So it's not in my realm of expertise to comment on that. But I think if you look at all the components, then you could come up with a design that's reasonable and feasible. You have to look at building safety, you look at evacuation, and that could mean outside or in safe places. And then you have the firefighting question. If you have a good answer for the first two questions, then your needs for a fast extinguishing of the fire becomes less, and you could live safely with something less.
Mm-hmm. Okay. Let's see. Okay, most AHJs address prescriptive fire resistance and structural performance in a very compartmented and highly disjointed fashion. I guess that's a comment, not a question. How do we get a structural fire safety plan, plan reviewers together to define their roles and identify critical performance criteria when these disciplines essentially speak different languages, the language of the code enforcer and the engineer, and then let's say the performance-based engineer, where you're not arguing about code compliance, you're looking at trying to look at testing and forecasting performance.
I mean, I think that's a really good question, right? And those are somewhat different jobs. I understand the challenge. And as we talked about before, even when as an AHJ, you might want to kind of bring that expertise in-house. And I would encourage bringing more expertise in-house, whatever AHJ we're talking to. It's the amount of knowledge out there is infinite. No AHJ can have all of it, right? So you want to have enough good people on the inside to be able to ask the right questions. And then you bring in the best out there as peer reviewers to make sure that the process is right. I think that's the best way you could go around that. The only other thing I can see here is the role of these conversations. And that's why I really do appreciate having this forum and being able to talk to people who are in that role as an AHJ, because it is important for them to also see what's on the other side, right? There has been this divorce between safety in fire and engineering. When it comes to structures, that's a 100-year divorce. It does take some time to get past that. But so these conversations hopefully lay out the groundwork for that. To me, the one thing that could be a really practical thing and it could drive the change is to look at buildings in two categories. Again, broad, typical buildings, and then special cases where the consequences are high. I think those are the structures where you want to have a focus and you want to ask tougher questions, and that's where you want to mandate more from, you want to ask more from the design team. If something is mandated, and to me that's a resilient design, whatever the hazard is. If a study of the resilience of a building and then having a resilience design as appropriate for that building is mandated for these high impact structures, that drives the engineering community to do more on that. That drives the AHJs to also deal with that, and they naturally go through that process, right? Everyone will get educated at the same time on the process, and then in the meantime, you are relying on expertise from outside and all that to improve the process and use them as third-party peer reviewers, or you could have advisory boards that broadly provide advice to departments of building or fire departments on, broadly speaking, this approach makes sense, or broadly speaking, don't look at this. This is just nonsense.
Mm-hmm. Yeah, and I don't know that there's structures in place really to pool that expertise, nationally or even internationally. And certainly, I think we've argued, or I've argued in the past, that this is a global, when you start talking super tall and in regard to high-rise buildings, it's really a global industry, and it ought to be internationalized so that we learn from the experience of others. And if you just look at things like, the facade fire problem, leaving aside Grenfell, but the UAE and Dubai and places like that, where we don't have really thorough investigation and intelligence on those fires, right? It's very piecemeal, and it doesn't seem to be systematic. So we got a question here, and I think I'll paraphrase this a little bit. Your superb presentation highlighted the fact that the World Trade Center failed in every single safety and performance aspect that you discussed. While the system made a lot of noise in response, I mean, you talk about the system there, I think what we're getting at is the reality, the political dynamics of the fact that AHJs work for local governments predominantly. Local governments are in the business of fostering development. And so there's kind of an inherent, I will say pressure, not judgmental, but just pressure in favor of approval for projects. And so I guess I'll twist it a little bit and say, how can we, as an AHJ, how can we leverage that or kind of counter that to make sure that it's for lack of a better term, everybody's on an equal basis in terms of making considerations for a design that's being proposed?
It might seem naive. I think facts are the best thing to go back to. If you could quantify why something works or why it doesn't work based on, based on science and engineering that you could, show and stand by, I think you can stand up to anyone and have that conversation. If I understand the context of the question, there's always a tension between the interests of the different people who are involved in the construction industry. And I think that's a healthy conflict that we have in life in general. There are different perspectives, right? Each side has to try to understand what's going on the other side, and at the same time focus on what's important. I think from an AHJ perspective, safety is important, right? That's something that you do not want to give up on, right? But you do want to have the right tools to be able to defend a position with facts, saying when you remove this or when you add this, this is its impact on safety. I'm talking about doubling or reducing by half the risk of something happening. Then you could really get into a discussion, right? On the other side, if something doesn't have, let's say something has a huge cost impact, but you can't quantify how it's improving performance, maybe there is a question on whether that's not the best use of our resources, right? As a society, we do want to use our resources better, because if that money doesn't go to a building, it goes to something else, and maybe that's a better use for it, right? So I think dialogue between AHJs, between designers, between construction industry, in the context of what we want to talk about, is important, because on one side, the AHJ wants to make sure that it's safe, but on the other side, I understand the skepticism, and there's a lot of times when someone might just want to push for something because it saves them a dime, but it also doesn't necessarily mean that if you force something that's cheaper or more, it's better, right? We want intelligent, rational design. I think that's in the interest of everyone, and that's where you could have a conversation with anyone. If you have a fact that says this thing is unsafe, and if I add this thing, it increases safety, I think that brings leverage with itself.
And let me build on that and just say, I think one of the concerns is that, and maybe comment on what is the role, or what's the legitimate role of local fire protection, let's say fire suppression capabilities and resources. So in other words, we take the identical building, we'll put it in Manhattan, and we'll put it in Lagos, or we'll put it in White Plains. And you've got totally different reaction once the bell rings on what you're going to get to. And so what role legitimately does that play in performance-based design?
I think that could be very relevant, right? It shows up in two ways. It shows up indirectly through what the AHJ approves or not, right? So New York would obviously be more strict on some things, because the consequences of a failure in New York are different from the consequences of a failure of the same building in the middle of nowhere, right?
Well, from a structural standpoint, maybe, but I'm thinking I would flip that around and say, to some degree, there's a bit of a moral hazard on the part of New York or a place like it, because we've got a big fire department. So
I know I want to address that side of it too. On the other side, New York has some resources, right? I don't think that resources are too much for the risk that we have. I can't quote by name, but I want to say there was a presentation from the fire department a year or two ago about fighting a fire in a high-rise, and the chief mentioned that it takes 100-something people to fight the fire in the high-rise. And that's not because we're New York and we have the resources. It's because that fire takes 100-something people. It's the needs of the fire, not the resources of the city. I think that's a really important message to have out there, right? So yes, I'm not advocating doing less in New York, but certainly if you're building something out there where you don't have the resources and the experiences of FDNY, absolutely you want to do all you can to minimize your risk even further. So if there is some allowance in New York for something, maybe you want to think about that twice if you're an AHJ in a smaller place that has these high rates. I think that comes into the question. But we do want to have that minimum baseline of safety for, for these high impact buildings. Again, that's the question. Look at your building, quantify your risk and potential consequences. Can you live with them and articulate them or not? If you can live with them in a public way, that's fine. That works for that area. If it's not acceptable, then maybe they should be doing something different.
Okay. We've got just over 5 minutes here. And so if this is your last shot, if you've got a question, particularly one in context of where we are in the discussion.
By the way, I don't mind staying longer. I know it's your time as well, but
yeah, no, I think we've got the. I can't recall when the Zoom link expires. I think it may be 3:30. So this one was said. Your examples involve a consideration of total burnout conditions. I've been involved in recent analyses that indicate that such conditions are far less likely to occur in modern office buildings due to dramatic changes in furnishing flammability and less paper. ASCE 7-16 Appendix E does not require a design fire based on total burnout. Where should we start? How big a fire is big enough for design purposes?
Good question. I'm not saying every building has to be designed for fire burnout. I'm saying the design has to look at what is acceptable for that building. There was a mention of ASC 7 Appendix E. That's the document that outlines the process for engineers. The minimum criteria is the building has to stand long enough for people to be able to evacuate safely. That's your minimum performance with safety margin on it, obviously. It's like people get out in 10 minutes, your building collapses in 11 minutes. That's not acceptable. But the minimum is you evacuate people safely. Okay, so now the question for a high-rise becomes, how long does it take for you to evacuate people safely? And the other criteria is if people are taking refuge in place, then that area should be able to resist fire burnout, right? So if you have a building and you have the right resources in terms of means of egress, in terms of fire department response, and in terms of fire protection measures where you can evacuate people safely in some duration of time, with the right safety margin, that's the minimum goal for the building, right? And that should be. I don't think anyone would say no, like in a case where people can collapse with buildings in it would be acceptable for these larger consequence cases. Smaller buildings, people can get out. For a really tall building, that could be a challenge, right? So it becomes a question. If you can evacuate in time, then maybe you have to design for a limited period of time. You still need to consider the context. I think failure of a high-rise building in the city is a bad idea, independent of whatever, but the prescriptive code doesn't require that either, right? So at least if you're trying to achieve what the code is presumably intending to get there, you have to do that much. Once you start looking at making your design resilient, it might not take as much to make it resilient to the full burnout. So once you start doing the job, getting it to there is not as much of a push, in my opinion. Depends on the case, but as a broad principle.
Okay, thank you, Ali. So I think I'm going to start wrapping things up here. We've got about 2.5 minutes. So I want to thank you very much. We got a remark from Gerald Tracy from FDNY. He said, thank you so much. Your presentation was outstanding. You're smart, articulate, humble, and answered our questions and thoughts honestly. And so I humbly
I appreciate that. I really do. So thank you so much.
He's a structural engineer with a heart, folks. And we're so happy that you were doing this, and it's really important. I sit on the high-rise building safety advisory committee for the NFPA, And there are real tensions there, and everybody's well-intended, and I think we're making some progress. But this dialogue between the engineering community and the fire service and the AHJs is really critical. And it's an area that's not going to go away. I think, as you point out quite persuasively, that we need to figure out how we're going to get where we need to be. And I think there's a lot of work in that area ahead of us. And so it would be good to see if the engineering and architecture community could actually join forces with kind of thoughtful people in the AHJ and fire service community to bring everybody along together and maybe develop a roadmap on the expertise and skills necessary for professional development, getting more fire protection engineers, getting more the notion of third party or peer review to be more common and more accepted across the country would be, I think, a very good thing. So with that, thank you very much. We did have a question. We will post a version of this online. We'll send an email out when that's available, probably be a couple of weeks. And so thank you all for attending. Please join our mailing list. We don't send a lot of messages, but we have fantastic talks, really no matter what your area of interest is. So once again, Ali, thank you very much. It was great, and we look forward to working with you going forward. And thanks again for taking time out to speak with us today.
Thank you for having me. I really enjoyed it, and I really appreciate the audience also sticking out for this long conversation and providing their feedback and questions. I enjoyed this, and feel free to also reach me if you want to have further discussions. This is a topic that I always like to talk about and I'm passionate about. So.
All right. Well, thank you very much. Thank you, everybody. Thanks for joining us, and have a good night.